Hello everyone, I am Sri Murari, and along with my teammates Sudarshan and Sneha, we built a project called Similar Image Finder. It is an AI-powered visual search engine that helps you find images that look similar just by uploading an image or giving a URL. Right now, most image searches depends on tags or keywords, but that means we need to label every image manually, which takes a lot of time, and it isn't always correct. Also, if an image has no label, it won't show up in the search results. So what if we want to search purely based on the content of the image itself? Our idea was simple. Let's allow people to search using images instead of words. You upload a photo and the system shows you other images that look similar. No need for the tags, file names, or labels. We use deep learning model called Flip made by OpenAI, which understands the image content at deep level. So here's how it works. You give an image, either upload it or paste a URL. We pass that image through Clip, which gives us a mathematical representation called an embedding. We store all the embeddings from the dataset. Then we use a technique called KNN to find embeddings that are closest to the one we just got. Finally, we show these images as output. Before going into the demo, I'd like to walk you through the code behind the model. So this is a notebook. It shows how we built, embed, and evaluated the image search step by step. We start by importing the required libraries like PyTorch, Clip, PIL, and scikit-learn and Matplotlib. These are the main tools that we need to build the model and analyze the result. Next, we load the images from our dataset. We used Unsplash Lite dataset and of over 21,000 images, as we mentioned before. Then we load the clip model using OpenAI's clip library. We use Vision Transformer B32 version, which is lightweight and fast. The model is loaded to either GPU or CPU based on the availability. This gives us two things, the model itself and the pre-processing steps we use on the images. We loop over all the images and pass them to through clip process pre-processing steps, and then we pass each image into the model to get its embedding. Then we save all the embeddings into the SAV file using Pickle. This makes loading faster during the Streamlit demo, which we don't where we don't need to recompute embeddings every time. Now, we fit KNN model using scikit-learn. It helps us quickly find the most similar images based on the cosine distance between the embeddings. We will be saving the model and also the image thumbnails along with the embeddings into the SAV file. So now we know how the system works. Let's talk about how we evaluated its performance, both quantitatively and qualitatively. From a quantitative perspective, we used two metrics, clip similarity score and intra-query diversity score. Clip similarity score measures the semantic similarity between query image and the top six retrieved images based on the clip embeddings. We computed cosine similarity between clip embedding to the input image and then the embeddings of the top six retrieved images. The average of them will be the clip similarity score. We have done this for 1,000 inputs, and the model has achieved an overall score of 0.9135. Since the score is close to 1, it indicates that the retrieved images are semantically very close to the input image. The His plot shows how close the retrieved images are to the input image. Most scores are high. The more they are close to 1, the more the retrieved images are semantically closer to the input image. The Bot's plot of slip similarities shows the overall spread of similarity scores. The scores are tightly packed near the top with an high median. The second metric is intra-query diversity score. It captures how genetically diverse the retrieved images are. We compute pairwise cosine similarity between the six retrieved images. A lower score means that the retrieved images are very similar to each other, while a higher score indicates a variety. We observed an average diversity score of 0.1078, suggesting that the results are consistent. The graph shows uh, how different the top six retrieved images are from each other. Most scores are low, meaning the images are consistent and not too varied. We combine the clip similarity score and the intra-query diversity score into a single scatter plot to better understand the relevance of retrieved images. The plot shown on the right side Each point represents a query. The x-axis shows the clip similarity score, and the y-axis shows the intra-query diversity score. The intra-query diversity score is inversely proportional to the clip similarity. So we have observed most of the points are in the bottom right area of the plot, which means the model is retrieving images that are both highly relevant and visually consistent with each other. To further support our evaluation, we have performed a TSNE-based cluster visualization on clip embeddings. We visualized over 2,000 images in 2D, along with the input image and the top six retrieved images. The retrieved images form a tight cluster around the input, clearly indicating visual similarity. This confirms the model retrieves meaningfully related images from the dataset. The graph shown on the screen shows 50 different input images and their top six matches projected in 2D using TSNE. Each query and its results form a small, tight cluster showing that the model finds closely related images. As the final and most relevant form of qualitative evaluation, we perform direct human inspection of the top six retrieved images for several inputs. We found that the retrieved images are very closely related to the input image in terms of what they show. The direct human check confirmed our model is working well and returns images that made sense and feel truly similar to the input image. The two images shown on the screen shows how well our model retrieves similar images. In the first example, the input is snow-covered mountains, and the top six images are also shows the snowy mountain peaks with similar colors and landscapes. In the second image, the input is a beach scene, and all the results include bright blue water, clear skies, and sandy beach similar to the input image. These examples show that our model understands this overall scene and content of the input image and find results that are visually and semantically related. Now I'll move on to show you the actual results live with our Streamlit app. First, I'll upload an image of a cityscape. When I hit the Find Similar Images button, you will see the model finding similarly looking city or landscape images. Next, let's paste a URL of an elephant. And the model will show similar images of elephants, even though there are no tags saying elephant, it just understands the image. Coming back to the slides, the key features are there are no manual labels that are needed. It's super fast and can scale to big data sets. It works with Streamlit or any front end easily and learns both visual patterns and meanings from the image, thanks to the clip. The system can be useful in many places, such as in many industries, such as in e-commerce industries to find similar products by image, in design and art industry to find the similar visuals, in education for education to group visual content. It can also help AI assistant with the smart image search and even duplicate detection. In future, we want to add natural language search. And real-time front end like in Streamlit, we won't be deploying completely. So a good front end with a React can help deploy our project without any backend needed. A way to also we can use this on a personal photo libraries or even massive datasets, and also integrate into chatbots or augmented reality apps. So to conclude, we built a similar image finder using Clip and KNN. It helps users visually without needing tags. It's fast, smart, and easy to use, and it has a lot of real-world applications. Thank you.